Welcome to the Explainer. All right, today we're going to tackle calculus. And look, forget all this scary stuff you've heard. At its heart, calculus is really just, well, it's the language the universe speaks. It's how we describe change, from a tiny raindrop falling to a massive planet orbiting the sun.
So, to really get why we even need this stuff, let's kick things off with a little puzzle. Think about this. Calculating your average speed on a road trip. Super easy, right? You just take the distance you went and divide it by the time it took. Done. But what about the exact speed your speedometer is showing at one single instant? That fleeting moment. Yeah, turns out, simple algebra, it just can't touch that question.
And right there, that speedometer problem, that shows us a huge gap in our usual math toolkit. See, we need something more than just formulas for things that are sitting still. We need a language for things that are moving. And that, my friends, is calculus. It was literally designed to describe a universe where, let's face it, everything is constantly on the move.
So algebra is awesome for snapshots, right? Static pictures. But that speedometer reading, that's a movie. It's totally dynamic. And to capture that, we've got to zoom in, way, way in, on a moment so tiny it's basically zero. The tool that lets us pull off this magic trick, well, that's the first big pillar of calculus.
Okay, so let's dive into this first big idea. It's called a limit. And honestly, it's this incredibly clever workaround that lets calculus look at a single instant without, completely breaking all the rules of math. The core idea behind a limit is actually super simple. Imagine you can't step on a specific spot on the floor because, I don't know, the math police will get you. A limit just says, okay, fine, let's just sneak up on it from both sides and see what number we're getting closer and closer to. It's all about figuring out the destination, even if you can never actually arrive. Okay, let's make this real with a classic example. You see this function here? If we try to be direct and just plug the number 2 into it, boom, the whole thing breaks. We get 0 divided by 0, which is just mathematical nonsense. It's undefined. It's like the function has this little pothole, a broken spot right at the exact place we want to investigate. So what do? Well, this is the key question that limits were invented to solve. Let's just forget about landing exactly on the number 2. What happens if we just, tiptoe towards it? All right, let's try it. Let's start by getting pretty close. What if we plug in 2.1 for x? The function spits out 4.1. Okay, that's interesting. But hey, we can get even closer than that, right? Okay, now let's try 2.01. That's 10 times closer to our little problem spot. And look at that, the output is 4.01. You're starting to see the pattern here, aren't you? As our input gets closer and closer to 2, the output is getting systematically closer to a very, very specific number. And that's it. That's our answer. We can say with confidence that the limit of this function as x gets closer to 2 is 4. And the coolest part? We never actually had to land on that broken spot. We just got infinitely close, and that told us everything we needed to know about where it was heading. So now that we have this superpower of getting infinitely close to a point, we can finally go back and solve that speedometer problem. And this brings us to probably the most famous tool in all of calculus, the derivative. Its whole job is to measure the rate of change at one single instant. This picture really says it all. See the secant line? It just slashes through the curve at 2 different points. The slope of that line gives you the average change between those points. Think average speed. But the tangent line? The tangent line is different. It just gently kisses the curve at one single point. The slope of that line, that's your instantaneous rate of change. And finding that slope, that's exactly what a derivative does. Okay, let's put this to work with a real-world example. Imagine we've got a tank, and it's filling up with water. And what we have here is a little table showing us how much water is in the tank at 9 minutes, 10 minutes, and 11 minutes. Now sure, we could find the average rate of change between minute 9 and minute 11, easy enough. But that's not what we're after. We want to know how fast it's filling up at exactly the 10-minute mark. We want that precise instantaneous flow rate. And that sounds like a job for the derivative. So that using a derivative, what we're really doing is finding the slope of the curve at that one single point in time. And the answer is 0.7 gallons per minute. So at the exact instant the clock hit 10 minutes, that was the flow rate. That was the slope of our tangent line right at that moment. Okay, so we've seen how derivatives are all about slicing and dicing a problem into these infinite tiny little moments. But
What if we wanted to go the other way? What if, instead of breaking things down, we wanted to add up an infinite number of tiny pieces to find out the grand total?
Well, for that, we turn to integration. It's the other side of the coin. Here's a good way to think about it. If a derivative is like looking at your speedometer to find your exact speed right now, integration is like adding up all those speedometer readings from your whole trip to figure out the total distance you've traveled.
So here's a new problem that is just perfect for integration. We've got another tank, but this time the flow rate isn't nice and steady. It's changing all the time. The question is, how much water in total flowed into that tank between the 20-minute mark and the 100-minute mark? And the way we solve this is by integrating that flow rate function. What that really means, visually, is that we're calculating the total area under the graph of the flow rate between those 2 points in time. And when we do that, we get our answer, 4,000 gallons. That's the total amount of water that was added during that entire period.
Okay, let's step back and put this all together. We've seen how derivatives are all about finding instantaneous rates of change, right? Slicing things up. And we've seen how integration is about finding the total accumulation, adding things up. And what this reveals is this beautiful, perfect symmetry right at the heart of calculus.
You can even think of it this way. Derivatives, at their core, are about division. I mean, finding a slope is just rise divided by run. Integration, on the other hand, is all about multiplication. Finding an area is just length times width. They are perfect opposites, perfect inverse operations. They're the two essential sides of the mathematics of change.
And this isn't just theory. This is the language that we use to model pretty much everything, from the chaos of financial markets to the precise trajectory of a rocket heading to space. It really is the mathematics of a world in motion. So here's my challenge to you. The next time you see something change, your speed in a car, the weather outside, the price of a stock, just ask yourself 2 questions. What is its rate of change at this exact instant? And what is its total accumulation over time? If you do that, congratulations, you're officially thinking in calculus.